Today's lab is identification of an unknown organic substance. And there are several ways you can go about determining what an unknown is. You've seen or been exposed to spectroscopy. If we take a look at mass spec, that's a type of analytical tool that we could use to determine the molecular weight of that substance. You have seen before UV vis spectroscopy, and in UV vis we're taking a look at degree of conjugation, if you will. That's one of the most important things we probably could get from that. You've taken a look at IR spectroscopy, which looks at functional groups that are present. You've also taken a look at NMR spectroscopy that deals with the carbon-hydrogen framework, where you could piece together, is it a CH next to a CH2, or is a CH2 next to a CH3, so on and so forth. And GC, chromatography, could be used if you knew retention times of different substances. You could use that to identify particular compounds. What we're going to do is make use of physical properties and also chemical testing. In terms of physical properties, you're looking at what that substance looks like. Is it a liquid? Is it a solid? What color is it? We're also going to take a look at physical properties such as density, boiling points, melting points if it's a solid. And then we can also take a look at the solubility testing, that where you take your substance and dissolve it in certain solutions, and then depending on whether it's soluble or insoluble, you can narrow down what that substance might be. In other words, what class of organic compounds that substance could be. The chemical testing, I'm going to say this, the worst thing that a student could do if they're trying to figure out what an unknown is to grab all the different chemical reagents for chemical testing and start testing them left and right, because there's no need to do every chemical test. And if you have a surplus of information, sometimes that can be misleading, and it can also be quite overwhelming to try to figure out what the data is telling you. So probably the best place to start is with solubility. And so what this flow chart does is it tells you you're going to first start with water, so you'll put some of your sample in a test tube and then add water to it. Kind of a general rule of thumb, about 30 milligrams in a milliliter of that substance. If it dissolves, we consider that to be soluble. If it doesn't, then we say it's insoluble. I usually don't weigh out liquids. I typically add liquids into these other aqueous solutions, and then sometimes it is hard to tell if it is soluble or not if you're using a very small amount. I typically add more to see if what I'm seeing on the top layer is a meniscus layer or is it actually a second layer. So we'll kind of talk about that when we get into the lab and actually do the experimental part. So let's say that we have our unknown substance and we put it in water. If that substance is soluble, whether if it's a solid, all the crystals dissolve, or if it's a liquid, we see one layer, then we're going to follow up this direction and we're going to measure the pH of that solution. If the pH is greater than 8, then that typically tells me I've got an amine, some type of low molecular weight substance. And again, think about organic compounds. There's not a great many of those that are water soluble. If they are, it's because they have anything, these functional groups like OHs or NHs that can hydrogen bond with water. So if I test the pH and it's 8 or greater, I'm going to think it's a low molecular weight amine. If it's somewhere less than 5, then first thing I'm thinking of is it's probably some low molecular weight carboxylic acid. If it's between 5 and 8, then I'm going to call that some type of neutral compound, low molecular weight. And if you think, well, you know, why is it 5? Sometimes distilled water or tap water can be around 5.5 or 6. So pH of 7 isn't always necessarily considered a neutral in terms of organic chemistry. So let's say that if it is one of these, then we know what other chemical tests we may want to do for these particular classes. And if it's neutral, that could be aldehydes, ketones, carbon-carbon, alcohols, I would say. Alcohols, aldehydes, ketones. If it was a low molecular weight ester, it would have to be fairly low, but that could fit in there as well. So let's say that if it's not soluble in water, or it's insoluble, then this is the route I'm going to go. I would next take another sample of it and dissolve it in sodium hydroxide, a 1.5 molar solution. If that happens to be soluble, then I'll take another test tube and treat that sample with 6.6 molar sodium bicarbonate. If that is soluble, then that tells me I have a higher molecular weight acid, carboxylic acid, or I could have a phenolic compound. And the asterisk here means that if you have phenol in general can be considered a weak acid. But if you have electron withdrawing groups on the phenolic ring, the benzene ring, like nitro groups or cyano groups, then typically what you will see is that it makes it that much stronger of an acid. So you notice you've got phenol in two places. This is where there's no substituents on that benzene ring to make it increase the acidity of the phenolic group. The asterisk means there are electron withdrawing groups on the benzene ring to increase the acidity. So if it happens to be insoluble, then most likely I would have some type of phenolic group. If it is insoluble in the sodium hydroxide, then I'll take another sample, treat it with 1.5 molar HCl. If that happens to be soluble, then I'm thinking that is a base, because we know bases like to interact with acids. And then that would be an amine. The difference here between what we see above is that this is a larger amine, where the number of carbon atoms in that structure dramatically reduces the solubility. Or if it was insoluble in the acid, I would take another sample and treat it with concentrated sulfuric acid. If it is soluble, then these are possible classes it could be, and it could be others. I'm just looking at the ones that we most likely would test. Could be a higher molecular weight carboxylic acid, aldehyde, ketone, alcohol, could be carbon-carbon double bond, carbon-carbon triple bond. And when you're looking at insolubility in sulfuric acid, if it's a liquid, certainly you're looking at two different layers. And it's not unusual for the solution to turn a little bit yellow. That's kind of normal. If it's insoluble, then I'm looking at alkanes, alkyl halides, just benzene ring, or halogenated benzene ring. So once I go through the solubility test, let's say that if I'm here and I think it's one of these classes, then there's no reason to do anything that a chemical test that would not involve these. I only want to focus on the chemical test that would involve these particular classes of compounds. Same thing here, if I know it's a carboxylic acid or phenol, I'd only focus on chemical tests that would deal with these two substances. There's no reason to worry about an aldehyde or ketone or alcohol if I think it's one of these compounds. So the solubility, it probably takes longer to do the solubility than it does the chemical testing, but in the long run, this would certainly be beneficial to you to take the time to do that, because you can weed out what classes it could be. I wanted to go over a list of chemical tests that we're going to be using. Certainly this isn't the only list of tests that you could do for different functional groups present in a compound, but based on the ones that we're going to be using, this is the only list of chemical reagents we would need. The top one, the ceric nitrate test, or some people call it the ceric ammonium nitrate test, that is a test that if it's positive, and here we're looking at color changes, this typically starts out as a yellow solution and then it may change to a red or red-brown. If we see that change, then typically we're looking at an alcohol. It doesn't distinguish one alcohol from another, meaning primary, secondary, tertiary. And there is some limitation of this test. This test is really only useful if your alcohol has 6 carbons or less in its structure, because we do try to dissolve that in water. So that could be an issue. You may get false negative tests just because of the size of the alcohol. So that's one particular test. There's another test, Lucas test, that can hopefully distinguish between primary, secondary, tertiary alcohols. The Lucas test, we dissolve our sample, or the reagent is a zinc chloride hydrochloric acid solution. And the mechanism of how that reagent interacts or reacts with these different classes of alcohols is based on an SN1 reaction. So what we're looking at is turbidity in the test tube, cloudiness. Typically a precipitate's not going to form, but it does get quite cloudy. So tertiary alcohols typically react the fastest, almost instantaneously. You'll see the turbidity. Secondary alcohols, typically not within 5 minutes, and then primary alcohols will never react no matter how long you have it in the test tube. Jones reagent, or I usually call it chromic acid test, one and the same. What that does, it is positive for primary, secondary alcohols. It is an oxidizing agent, so primary, secondary alcohols can undergo a chemical reaction with that reagent, as well as aldehydes. So if you got a positive test, you can't just say I've got an alcohol, because there is the possibility that it could also be an aldehyde group. It does not distinguish between primary and secondary. And let me just say this too, sometimes when you do a chemical test and it's negative, you can get just as much information if it is negative as if it's positive, because if it is negative, you know what you don't have within that structure. Tollens test is a neat one. It is also an oxidation test that works for aldehyde groups. Some people call it the silver mirror test. If the reagent is fresh enough and if your test tube is clean or flask, whatever you're doing the experiment in, the silver that forms will actually coat the test tube or the flask, and you can actually see your reflection in that. 2,4-DNP, the dinitrophenylhydrazine test. This is positive for aldehydes and ketones. So let me just kind of go back up here, because we've seen others that have aldehyde in it as well. Let's say that you think you have an aldehyde group, or you don't know if it's a primary, secondary alcohol or an aldehyde. So a test that you could do could be the 2,4-DNP or the tollens. I'm just going to focus in on the 2,4-DNP. And that is also positive for aldehydes, but not for alcohols. So you could, again, eliminate, if it was negative, then you pretty much know, well, it can't be an aldehyde group. And then iodoform test, that is a neat test. When you carried out, what you're forming is a yellow precipitate. And it's positive if you have methyl ketones. And what I mean by a methyl ketone, that means the methyl group has to be adjacent to the carbonyl carbon. So this is positive for methyl ketones, methyl aldehydes. It's also positive for ethanol. And the reason it's positive for ethanol is that it actually oxidizes to this substance, actually ethanal, if you will, and then ethanol would react, and that's the reason you would see a positive test. Or it can react with secondary methyl alcohols, and what I mean by that, here's our secondary alcohol. We've got a carbon bonded to the OH, and that carbon's bonded to 2 other carbons. If one of those carbons is a methyl group, then that would also give rise to a positive test. So iodoform test, you're looking for yellow precipitate. The solution turns out brown initially, but then the brown color typically disappears and you see a yellow precipitate. For the 2,4-DNP test, we're looking at a precipitate. That color could range from yellow to orange to reddish in color, really depends on the organic compound you're using. Again, Tollens test, we're looking for that silver mirror. If a silver mirror doesn't form, sometimes it looks like you've got a dark precipitate that's settling out, which would be a positive test also. Jones reagent, you've seen before, the orange solution, if there is a reaction, it turns that orange color disappears, and then you form that blue-green kind of precipitate. Again, what we mentioned here was the cloudiness or turbidity. And then the ceric ammonium nitrate test, we're looking for a color change from yellow to red-brown. I will say this, that if for some reason your alcohol doesn't happen to dissolve, you may see 2 layers, and that's okay if you see 2 layers, but if one of the layers has that reddish color, then we're going to say that's a positive test. Just having 2 layers isn't positive for the ceric ammonium nitrate test, but if one of those happens to be colored red-brown, that would be a positive test. Now, again, notice that what we're looking at here, we're not including esters or carboxylic acids here or amides. If you have esters and amides, those particular compounds, there's really no chemical test that you can use to identify those. What you have to do is a hydrolysis test and then isolate what you've formed in the hydrolysis step. Not looking at carbon-carbon double bonds or triple bonds here. We could have included those. They wouldn't react with these particular reagents, but we would have added others if we needed to. What you will also be given is when we go into the lab and I do these chemical testing, I'm not going to walk you through it so much and say what you have. I just want to make sure you notice what the change is, because I want you to go back and figure out what functional group you have. So I won't say, oh, well, the Jones reagent was positive, what does that mean? I've just told you what it means, so I want you to go back and look at that and figure out, use all this information and figure out what type of functional group you have. Once you have the functional group, and again, I'll have some boiling point information or melting point if it's solid. I'll have density information provided. You may have to calculate that density, but you can do that. Once you figure out what functional group you have, the chemical formula would also be given. And what I'd like for students to do is, once they have that chemical formula, based on what information they've obtained in the lab, they could write all different isomers of that compound with that chemical formula, and then look up physical data such as densities and boiling points, things of that type. And if you've got more than one possible structure your unknown could be, then you need to compare your physical data with what you got from the literature of all those different isomers, and then narrow it down to which one matches closest to that.